Good morning or good afternoon, good evening, depending on where you're signing in from. Welcome to the Maple Conference 2024. My name is Paulina Chin. I'm a senior architect here at MapleSoft. Dr. Kashka Kowalska and I are your contributed program co-chairs. This year's conference is once again full of great presentations from the Maple community and the MapleSoft staff. So thank you all for sharing your experiences and your expertise with us. I'd like to begin the conference with a land acknowledgement. MapleSoft's headquarters is located in Waterloo, Ontario, Canada. We acknowledge that Waterloo region, including the 3 cities and 4 townships, is located on the traditional territory of the Haudenosaunee, Anishinaabe, and Neutral people. We acknowledge the enduring presence of the Indigenous people with whom we share this land, their achievements, and their contributions to our community. We offer this acknowledgement as an act of reconciliation between Indigenous and non-Indigenous peoples of Canada. Now, I have a few housekeeping notes to mention before we get to our keynote speaker. The conference program is listed on our website. You'll find the link in the lobby, and we really have a great conference program this year, so please check that out. The recordings will be available after the conference. You can sign back into the conference platform to access them until November 30th, and then we'll add them to our website in a few weeks. If you're going to a session and it says it's in progress, but it's before the scheduled start time, don't worry, it hasn't started yet. It just means that the Zoom room has opened for the presenters. If you enter, you'll be put in the waiting room, and please wait, and then you'll be allowed into the room when it's time. And with that, we're ready for our first session of the day. Please note that all questions for the keynote speaker should go into the Q&A window. And now I have the honor of introducing Dr. Laurent Bernardin, President and CEO of MapleSoft. Laurent received his PhD at ETH Zurich in Switzerland after studying with Gaston Gonnet, one of Maple's co-founders. Laurent will be talking to us about the impact of artificial intelligence on the greater math community. Laurent brings a wealth of experience to the subject. He has contributed to the development of Maple for almost 3 decades, first starting as a student intern and then eventually taking the helm as president and CEO in 2019. And during that time, he has witnessed firsthand the evolution of mathematical software and the emergence of large language models. And he has been deeply involved in exploring how these different technologies can complement each other. I've known Laurent for, I think, almost 25 years now, and I've always appreciated his ambitious vision for MapleSoft and his unwavering belief in our motto, Math Matters. And with that, I'd like to invite Laurent to tell us about the impact of AI on the math community. Welcome, Laurent.
Thank you for the kind words, Paulina. And hello, everybody. I would also like to welcome all of you to this year's Maple conference. We have a record number of attendees this year. We have, as Paulina already said, we have an agenda that's packed with really amazing presentations. So I hope that you will enjoy these 2 days with us. Also would like to note that towards the end of this talk, we have an announcement to make. We will be announcing for the first time today a new MapleSoft offering, a new kind of MapleSoft offering, if you will. So stay tuned for that towards the end of this session. But first, we'll talk about AI, and we'll talk about the impact of AI on the field of mathematics. Let's see. So this slide I put up because I just wanted to remind everybody and draw your attention to just the astounding progress that AI technologies have made. I mean, way back, this is a screenshot from ELIZA, which was kind of one of the first chatbots that was labeled as a step towards artificial intelligence back in the 1960s. And also in the 1950s, there was this emergent concept of the Turing test that once a computer is able to mimic a human in a conversation, right, where you wouldn't be able to tell whether you are chatting with a human or with a computer, that's when kind of the artificial intelligence would have reached a threshold where it's human-like, right? Of course, now we know that's not quite true. I mean, tools, large language models like ChatGPT and others, and they do a pretty good job at mimicking a human these days, but that doesn't mean that they are truly intelligent. So we raised the standards, but just to illustrate again, right, how far these tools have come, and if you've ever played with one of those large language models, it's pretty astounding what they can do today. So when it comes to mathematics, there's lots of news headlines around this stuff, like Google DeepMind announced a few weeks ago that their AIs have solved 4 out of 6 problems from the International Mathematical Olympiad, right? So definitely a big milestones that we are achieving, and that's progress is made almost daily in this area. Another piece of headline from OpenAI that their new language models are now presumably able to perform complex reasoning tasks. Terence Tao, the well-known mathematician, recently said that when talking about ChatGPT, that he thinks they're now on par with a mediocre but not completely incompetent graduate student, which may sound like a put-down, but it's actually a huge compliment to these large language models. And so a lot of progress. There's a lot of hype too, right? A lot going on. A lot of very big statements being made, and if we continue at this current rate of progress, right? It's not clear where this will all end up. You also have some progress in the here and now that you can touch, right? So, for example, I might be biased here, but you download the Maple Calculator app, and you now have, using AI in addition to Maple's mathematical engine, and it's useful today, and it helps you today. The Maple Calculator uses AI, for example, to recognize handwritten pieces of mathematics, and it's astoundingly good at this. And even my very poor handwriting, it doesn't have much trouble recognizing and turning into math that you then can compute with. More recently, also the Maple Calculator can now solve word problems, again by recognizing the text and then sending it to a large language model that will analyze it and give you an answer. So tremendous progress in this area. Now it's not all rainbows, you know. So here's an example where we maybe see some of the limitations. So this is from a post on X on Twitter, where somebody is trying to use a language model to multiply multi-digit integers, right? And kind of see that if the numbers are small, you have a pretty good rate of accuracy, but the bigger the numbers get, the more often the result will just be plain wrong. So you can kind of see that there's limits here, and I think the underlying thread, and we'll come back to this a few times in this talk, is when do you want to use an algorithm, and when do you want to use a large language model? And we'll come back to this, but here's another example. Factoring a polynomial. We have a polynomial, x cubed minus x squared minus 10x minus 8. We want to find the factors. Here on the top left, you can see we give this to Maple, we get an answer right away, right? These are the factors. And that's easy and that's good, but it's also a bit of a black box, right? I mean, if we were a student trying to learn about factorization, this would give us an answer, but it wouldn't give us really any further insight into how to do it. But you can also ask Maple to give us an answer step by step, right? So this is using the factor steps command in Maple, and the output is actually produced as a document in Maple Learn, so we can view it online. And this is what Maple gives you, right? So a nice step-by-step procedure how this particular polynomial gets factored, right? And it uses a method that you might teach in a high school class. It looks at the constant coefficient factors of it, right? So it gives you some candidates, does a trial division, then does a polynomial division to get the rest of it, ends up with a quadratic, and skipping some steps here so that it all fits in one screen, but you find a common factor, and then that gives you your answer. Now, in the first case here, where we just get an answer, Maple obviously uses an algorithm to calculate the answer. The step-by-step solution that Maple gives is also algorithmic in the sense that Maple will build a decision tree, mimic somebody doing this by hand with pen and paper, and every step of the way do a calculation to see what the next step will be. Okay, so now let's look at what an LLM does with something like this. Right? So we'll ask the same question to ChatGPT. So factor this, and we get an answer. Again, we get a step-by-step solution. At the bottom, we get the factorization. We get the same factorization in all three cases. So the answer is the same. How we get there is very different. So this answer from ChatGPT was not produced by an algorithm, but it's a result that's produced token by token by using a deep learning network. Right? So you can argue which one is better. I think they all both give you the steps, right? Maybe you don't have the nice polynomial division. And maybe at the end also it just says that we need to factor a quadratic, and it gives you the factorization. Doesn't really go into how you do that. But either way, I think both are good step-by-step solutions of this problem. But again, keep in mind, same results, but very different methods being used. So let's make the example slightly more difficult. All right, so now we have a quartic here, x to the 4 plus 2x squared plus x plus 2. Maple factors it into two quadratics pretty easily, right? And but now we're going to ask Maple for the step-by-step solution for this. And this is what you will get. Right? Maple says, well, the steps to solving this really is go to Maple, use the factor command, and here's the factorization, and that's it. And that might be surprising at first, but if you think about it, this is not a problem that you really want to ever do by hand. And if you go back to the Maple factor command and you open the box and you look inside what's going on here, there's a lot going on, right? So to factor something like this, Maple will take the polynomial, project it modulo a prime, do the factorization over that finite field, which involves constructing a matrix, finding a null space, and it's a very involved process that you probably never want to do by hand. This is a case where Maple, to solve these kinds of problems, does not use any kind of process that you would be taught in high school or university. And hence the step-by-step says, well, we don't really have steps here because you wouldn't want to see those steps. All right, so let's try an LLM. Let's see what ChatGPT says about this. And well, here we give it the same polynomial to factor, and it says, okay, there's 5 steps, 1, 2, 3, 4, 5. There's the factorization done. Okay, so that looks great. But then let's look at those steps. So the first 2 steps, after the first 2 steps, it says, well, this doesn't really work. Let's try a different approach. So it tries a different approach, and then it says, well, this doesn't work either. Let's try something else. And it has step 4 here, where it finds that, okay, there's a common factor of x squared plus 1 that I can pull out. Okay, so that's a factor. So that's a factorization here. So we get an answer. First problem is that this is the wrong answer. Right? So because this x squared plus 1 actually is not the common factor. So already this line here is just completely wrong. How did ChatGPT get to this? I can only guess, right? But it's probably that this is a pattern for solving these kinds of problems that for some polynomials will work, right? Sometimes you can find a common factor like this and pull it out. And in the training data, there's probably several examples, right, where this kind of pattern of solving this kind of problem has worked. So it's being applied here, but unfortunately it's not applicable, and it doesn't work, and you get the wrong answer. But you get the wrong answer, but as usual with these LLMs, right, they give you a wrong answer, but sounding very confident about the result. So again, another hint here, right? That algorithms versus LLM, you have to be very careful. And that's kind of one takeaway from today, that I hope, if you forget everything else that I'll say today, please remember this. If there is a deterministic algorithm to solve a problem, use it. Don't try to use AI. Right? You get into it. There's problems with accuracy, right? We saw that in the multiplication example earlier on. There's reliability, like for the factoring example, right? That we can't really rely on the result being correct. There's a huge efficiency concern, right? If you think about that, back to the example of using an LLM to multiply 2 integers. Something like GPT-4 uses 500 trillion operations to produce 1 token. And so it's a flabbergasting waste of compute cycles to use an LLM like that to multiply 2 integers that you can do a lot faster. Right? And associated with that, right, the power consumption of running an LLM, right, is if you misuse it, if you use it instead of just using an algorithm that is fast and efficient, right? So there's a huge difference and a lot of waste going on. So that's definitely one key takeaway from this presentation, right? If there is an algorithm, use it. Don't try to apply an LLM. there's some corollaries to this. So on one hand, think that these types of AIs, LLMs, but generally, they're good at the sorts of problems that humans are good at. And they're not good at problems that humans would struggle with. So examples, right? I mean, if you had to multiply two 50-digit numbers, for example, right? You wouldn't try to do that by hand. You would turn to Maple or calculator or whatever, right? You would use a tool to do that, because humans are not good with just the bookkeeping process of doing a complex algorithm in their head. And neither are AIs, neither are LLMs. Right? You just have too short a window of what they're looking at to be able to do a complex iterative process and get a reliable result. And the other hand, right, problems that humans are really good at, like looking at a word problem and figuring out what the equations are behind it, that's also the sort of thing that LLMs are really good at today. So another corollary of this is that when it comes to math, we humans, we need tools to supplement our thinking. We have Maple, for example, right? I mean, to help us solve problems where we partition up the task in a sense, right? And we let Maple do the things that it's good at, and we use our brains for the rest. And the same is true for AIs. AIs will need the same tools. And AIs are good at the sort of things that humans are good at, and not at the things where humans need tools, right? It's natural consequence that we need to couple these things. We need to use LLMs to interpret the language, and to do the modeling, perhaps, figure out what the equations are, and then we use a calculation engine to do the math. And those are sort of experiments and projects that we at Maplesoft are definitely in the midst of. So a consequence of the statement that AI is good at the sorts of problems that humans are good at kind of sets it up as a bit of a competition. You know, if humans and LLMs are good at the same sort of things, right? So what are the limits? And what's the role of the human? What's the role of the mathematician going forward? And hence, what's the role of math education? What do we need to teach the next generation of mathematicians? And so I think those are the really big questions. The way I think about it is that if I take mathematics, at the core of it, we have calculations. And it's kind of the step-by-step rote arithmetic, solving equation, right? Manipulating, doing algebra, all that sorts of stuff at the very base fundamental layer of mathematics. That's what we find. And then one level up, we have the modeling tasks, right? And modeling for me connects the real world with the underlying equations. So word problems are a simple example of this. You look at a real world problem, and by modeling, you discover what the underlying equations are that will help you solve this problem. And then the other way around too. Also part of modeling is you get a result, you get an answer from the calculation side, and now what does it mean? How does this help us in the context that we pose the problem? then we go one step up into insight. And so here we've done the modeling, we've got an answer, we solved the problem, but now the question is, okay, what does this really mean? What does this really mean? What can we learn from it? And what's the next question that we need to ask? Then I think at the very top is in mathematics is the creativity, right? Where we come up with new ways of looking at things, of new mathematical tools in our tool chests, right? That need to be discovered, that need to be created. Right? So that's kind of my view of how I would break up the field of mathematics into those four very broad categories. And of course, it's way oversimplified, right? But it gives you a kind of a model of thinking about this. Sometimes people also talk about reasoning, and especially in the LLM context, right? Reasoning models. So reasoning for me is an iterative loop between modeling and calculations, right? So you model something, you calculate, you get an answer, and which gets, and then you think about, okay, what does this mean? And you get back to modeling using the results that you just discovered, and it's a loop on this side. And I think that's also what people mean when they talk about reasoning LLMs. Right? There's a loop that where they find an answer and then go back and iterate over that answer. Okay, so now talk about the human versus machine, kind of the competition that we're setting up between LLMs and mathematicians. You know, and this is not really anything new. Think about it, right? When first we had mechanical calculators, electronic calculators, tools like Maple, what happened is that it allowed us to move up this scale, because calculations could now be done using a tool. It allowed us to focus more on the modeling tasks. Doesn't mean that we stop teaching arithmetic, right? Because it's still and always will be important to understand how that works and what the fundamentals are. But it allows us now, because we have tools, we can move beyond that. We can rely on tools. We focus one level up. And I think today's LLMs are getting really good at the modeling tasks. And you can argue how good, right? But it doesn't really matter, right? They're doing really well on simple problems, and they're getting better every day, right? So at some point, I think modeling, LLMs will be the tools for modeling, just like calculators are the tools for doing arithmetic and simple calculations. And for us humans, you know, that just means, I think, that we need to shift up again. And so we now have tools that can deal with calculations and the modeling task. And now it's about, okay, we focus on the insight behind the math. And we focus on the creativity of okay, where can we take this? What can we do with this? You know? And it's an opportunity, right? So it starts as a competition. I don't see it as a competition. I see it as the tools that are available to us are getting better and better, and will be able to do more as a result. For math education, it doesn't mean we will stop teaching modeling, just as it doesn't, calculus didn't mean that we stopped teaching arithmetic. Right? Always be important to fully understand the fundamentals that we built. But then you can rely on tools to make it easier and to be able to do more complicated things, do more exciting things. And of course, right, I mean, MapleSoft will be with you in all these steps. And tools like Maple, like the calculator, like Maple Learn, and they definitely help you with your calculations. We are already integrating LLMs into our tools to support the modeling process. And then inside creativity, right? That's where a lot of the focus will shift to. And you'll always need the tools that will support you in both that endeavor, but also in teaching that right? Because education will have to evolve with this. And I think education will focus more on insight and more on creativity as this unfolds. Okay. Back to the here and now. And so first off, there is a session today, not right after this talk, but the following one, where you can learn more about how our tools, how MapleSoft's tools use AI today. Right, so there's a lot of AI in Maple today, in the calculator, in Maple Learn, right? And this session will tell you more details about what's available to you as a tool chest today. And of course, I mean, students are still struggling with maths, and maths remains actually a major cause of students dropping out. And our mission at MapleSoft has always been to help students learn, help instructors teach. We want our technology to be available to as many people around the globe as possible. That's why we launched the calculator. That's why we launched the online Maple Learn product. Our technology is used by millions of people around the world today, and that's really our mission to make that process easier, to have a positive impact on more and more people. And AI increases the opportunities, I think, to have that impact. So at the beginning of this, I said that we would be announcing a new initiative at MapleSoft. And so and this is about I mentioned that math can be a real stumbling block for students. So especially first-year students, their success in them, whether they are studying math or studying anything else, right? Often there is a first-year math course, and often it's a real obstacle, right? And so student success is really critical, and that's a major focus of what we as a company are looking at, right? Difficulty in math is a big driver of this. So again, right, our mission is to helping those first-year students, and our new initiative is really focused on that particular task. With that, we want to level the readiness playing field, right? Students coming into a first-year university program often have very different levels of being ready for that math course. We want to boost understanding, want to increase their confidence, reduce anxiety, again, in that critical first year. Want to make sure that we can help students when and where they need the help. And also we want to give more insight to the instructors in terms of where are their students struggling. So the student success platform. We go through this. So it starts with the student studying, maybe doing an assignment, working on their homework, right? Working towards an assessment of some sort. And they will have the Maple Calculator mobile app at their disposal to help them out. So student works on a problem, has difficulty, is stuck, can turn to the Maple Calculator app, either type in the problem or take a picture of the question and get an answer. Oftentimes get a step-by-step solution, and you get a graph to get a better understanding what's going on here, right? So the Maple Calculator app will help that student out. Now, you might say, well, there's hundreds of tools like that available to a student, and that's true. And there's so many resources floating around the internet that a student can use to just get an answer or get a step-by-step solution and get themselves unstuck, right? So and it's also a little bit of a problem, right? Because as an instructor, when a student submits their homework, say, you no longer really know how much they did on their own and how much did they just rely on some tool out there, and give them the answer, copy it down, and move on. And so you have, as an instructor, this creates a real problem, that you no longer sure what the student's knowledge level actually is. So to make the calculator app is presumably the same, right? You would they use the app, get a solution, and it's they could use that to cheat. But that's not why we built the Maple Calculator. We built the Maple Calculator to help the students, get them unstuck, reduce frustration that's building up by being stuck, help them get understanding what's going on with this, help them learn. And in addition, with the new student success platform, we're now able to track what those students are doing with the app. And we're not doing this student by student. We're doing it as an aggregate measure of a class, right? So that means as an instructor, you'll get insight into how is your class using this app? What kinds of problems are they struggling with? Where are they asking for step-by-step solutions? What sorts of problems are they trying to solve? What are they engaging in? And how much do they rely on a tool when they do their work? So big difference here is that it removes the black box problem. Students have access to a tool to help them, but now we get the insight into what are they doing, what are they struggling with, what's their real level of understanding. And then we can use that data from the app, and that's the middle piece here, and we can now create resources that will help those students. And that's something that we've always done, right? Maple has been used for over 30 years to as a tool to help students dig into particular areas of struggle, into doing visualization to get more insight into something, to try to illustrate how to solve a problem, and what does it mean, and why do we do it this way, right? All those sorts of things. But now, because we have the data from the student activity in the app, we can tailor those resources to the class needs. And then those resources will then be available for the students to in addition to their work that they doing to try to solve their problems, right? Now we know, okay, you should look at these resources, you should do these exercises, right? Because that will help you understand, because that's what you're struggling with, and that will get you through that course, and that will make you successful. So that is the crux of the new MapleSoft Student Success Platform. And that was a very quick overview. We do have a session tomorrow at 12 EST, where we're going to discuss this new platform in a lot more detail. So please join us then. I'm at the end of my time here, but very happy to answer any kind of questions that you might have.
Hey, thank you, Laurent, for opening the conference with this very important and extremely timely topic. I'm going to ask the audience, if you have more questions for Laurent, please type them into the chat window and I will relay them. In the meantime, I'm going to read out some of the questions that have already been put into the chat, Laurent. Some of them have already been answered by other members of the chat, so I'm going to skip over some of them that have been answered. But one that is interesting is, when the answer isn't known, how does one debug AI with Maple?
How does one debug AI with Maple? That's a big question. I mean, AI can mean different things, right? So if you mean how does one debug how an LLM produces an answer, wrong or right, with Maple, I think the first question is, how do you debug an LLM, period? And I think that is still a research problem, because these systems are very much black boxes. What we are looking at MapleSoft is to put guardrails around using an LLM, in the sense that you use an LLM to answer a question, but when the LLM comes to a point where they need a calculation, well, they should delegate that calculation to Maple. Maple will perform it using the algorithm, will give you a correct result, and then that answer then comes back into the LLM, which then proceeds with its producing the answer. But every time it comes to a point where we need an algorithm, it will defer to Maple, come back and proceed, right? So that is going to make the LLMs a lot more reliable, not foolproof, but a lot more reliable than they are today.
Okay. All right. So let's see. So you were talking about deterministic algorithms. Someone asked about the deterministic algorithms in your talk, and contrasting with stochastic algorithms, but I'm going to jump to another question which is related, where person submitted it said comparisons with ChatGPT in case of deterministic algorithms are interesting, but have you tested the comparison between Maple and Prolog-based math problem solvers, which in turn can help narrow the bug search in LLM? So general question about deterministic algorithms compared to some of these other options.
Yeah, I mean, something like Prolog is still an algorithm, right? So it doesn't really matter what programming language you use to implement your algorithm. If it's deterministic algorithm, it's deterministic, and it will stay deterministic, right? So I think maybe I don't fully understand the question. If you're asking whether we've compared this to maybe the theory improver world, right? Maybe that's a different way to look at it, where I think theory improvers are much more alike what the LM will do to solve the problem, except that they have a long history of connecting with a mathematical engine already, right? So a theory improver will typically go through some reasoning steps in quotes, but will defer to a computational engine as needed, in this case, not for accuracy, but for efficiency.
All right. Let's see. There's another question. I'm not sure I understood it completely, but since we have our model Math Matters, one of our attendees asked about people getting math smarter and whether AI's telling people, giving more information about these math problems and improving their capabilities, will people get math smarter? I think that's what the question is asking.
Yeah, I think the answer is yes, right? Because the more tools you have available to do the fundamentals, right? The more you can build on top of it and get a better understanding and get smarter about it, if you will, right? Because say for example, right? I mean, something like Maple has allowed us, when we teach math, to have a tool chest that allows us now to look at more complicated real world problems that we can solve that we otherwise couldn't, because we would get stuck in just the grunt work of doing complicated calculations, as opposed to focusing on how can we use those calculations, what do they mean, where can they take us. And I see LLMs just taking that one level further, right? The tools get better, we can solve bigger problems, we can teach bigger problems, and we can connect it more to the world around us.
Okay, great. So someone has asked about LLMs as pattern recognition models, and does it make sense to express reasoning as a pattern recognition problem?
Yeah, I mean, the answer is I don't know, but and I think nobody knows, but you can argue that maybe when we reason, right, it's very much a pattern recognition problem, right? We think about what have we encountered in the past, and how can we apply the lessons that we learned, our experience, to this new problem, right? So it's very much a pattern recognition problem, I think, right? And as I mentioned before, the reasoning comes in then by iterating that, by taking our past experiences, seeing how we can apply that to a new problem in front of us, making progress, and then iterating over that, and then step by step getting a sense of what does this mean, and what new things can we learn from it. But it's very much, I think, an iterative process.
Okay. There have been a number of comments thanking you for the talk and saying that it was very inspiring, informative, and so I hope you'll read all the details in the chat. There's some longer questions too. One was about with details about research study on related to AI, but there was an interesting question in there about mathematical science's lack of consensus on competencies required to incorporate AI effectively in mathematical research without negatively affecting research integrity. Do you have any comments on that?
Yeah, I mean, it's a complicated question, of course. I think on one hand, it's pretty clear that, at least for today's state of the art, you can never take an AI and LLM at face value. You always have to double check, right? So you can never base a new result solely on what an LLM told you, right? I think that's pretty obvious, right? We don't trust these systems because they get things wrong. But so that's one aspect of it. But I also want to draw your attention to the fact that it's very much like we humans in the sense that we all make mistakes, right? None of us is 100% reliable all the time, right? So collaborating with or using an AI in your research is very much like having a collaborator, right? It's just the only difference is the level of competency. And as the LLMs will get better, I think maybe the difference will get smaller. I don't know how far we can push this, right? But it's not so different from working together with a human being.
There's a question also about neural nets. Any possibility of that in Maple? It was mentioned in the MATLAB context, and any possibilities for such a thing to connect to Maple Sim?
Yeah. I mean, there's lots of opportunity here, and if you go to the following talk on leveraging AI, you'll see what kind of tools Maple has today. For example, there is a copy of TensorFlow and built into Maple, right? So you can build your neural nets right and run them right from within Maple and kind of connect the mathematics with a neural net. So there's lots of opportunities for doing things together. On the Maple Sim side, where we're talking about simulating engineering systems, there's lots of research going into physics-informed neural networks, for example, right? Where you set up an AI, a neural network to solve a problem, but it has this physics engine that keeps it honest, which is very similar to an LLM having a math engine to keep it honest. So there's lots of opportunities in it.
Okay, great. We're almost out of time, so I'm going to ask one last question, which is actually probably more related to your final thoughts on our future SSP platform. About whether there's evidence that beginning students at a college university level who use Maple, say in a calculus or other course, learn mathematics better than those who do not use it. What are your thoughts and experiences with that?
Yeah, I mean, we have lots of experience. I've been doing this for 30 years now, right? And I think the consensus is that yes, absolutely, students learn better when they have the right tools to help them, right? For a variety of reasons. You have a tool, you can overcome obstacles, right? You don't get stuck. You can you're not limited to looking at problems that you've given from your instructor or from an expert, you can make up your own. You can take it further. You can use visualization techniques and interactive techniques to make that math come alive, make it more engaging, right? Get a better understanding of what's behind it. Right? There's so many opportunities for technology like Maple to make learning better and produce ultimately graduates that have better understanding of the mathematics, but also a better appreciation of what they can do and what the power of math can bring to them.
Okay, that's a good place to end. And I'm very sorry that we did not get to all the questions in the chat. There are a number of large number of comments there. However, you're going to have another opportunity to chat with Laurent or about this presentation or any other topic. We have a lunch with the CEO session at 12:30 today. And so I'm going to take this opportunity. Thank you again, Laurent, for the very interesting and thought-provoking talk.
Thank you, Paulina, and thanks for everybody who joined us today. I hope you have a great rest of the Maple conference.
Now we're going to take a short break. We'll resume the conference at 10:15 with a product presentation. Paul DeMarco will walk you through some of the Maple 2024 gems you might have missed. You definitely don't want to miss this talk, so I hope to see you all then. Thank you.